The last two are where I really started getting into the details here with this more detailed book. So the first chapter was about using input data, and all I've done is taken the projects in this book and greatly simplified them, which is what most of my projects are, so people that want to learn in like a hands-on CTF fashion can get an idea of what's going on pretty much faster. So I'm here, check to make sure you have the right versions of things, which is normal stuff, and then you download the data. Here we're downloading data from a GitHub place that has housing data. What we're getting here is California housing price data. It broke California into little zones, like little counties, although they're smaller than counties, and it figured out the housing price in all those areas. So here's the data set. If you input the data, it comes as a tarball and you unzip it, and here's the structure of it. You have latitude and longitude, and then the age of the house, the rooms, bedrooms, population of this area, the number of households in this area, the income, house value, and ocean proximity. All these are floating point numbers, but ocean proximity is not. So this is the 10 columns in the data, and I have, as you see, 20,000 entries. You have 20,000 records to map all of California. And you can use the head function to see the first few records, and there they are. Scroll to the right, you can see that the ocean proximity is words, and the rest are all numbers, like house value, median income, population, and so on. All right? And so you can also see the count of, I'm going to look at that ocean proximity. Here's the possible values of ocean proximity: island, near bay, near ocean, inland, and whatever this means, less than 1 ocean. I'm not sure what that means. But those 5 possible values, and that's how many records, zones, districts, they're calling it, have this. So you can also call the describe function to get a summary of the data this way, and it will show you the count, the mean, the standard deviation, and other numbers so you understand what happens here: latitude, longitude, latitude, median age, input, and so on. These are useful things to get an idea what you have in a data set. Nice ways to see what kind of data exists. And so you might also want to make histograms, and it's very simple to do that, just a few lines of code. You can make histograms of the data, and so here's the longitude distribution, which shows, I think, as you might expect, longitude and latitude are binding, and I think the point is there are really 2 big centers in San Francisco. There's the Bay Area and near Los Angeles, so there are really just 2 places that have most of the data. And that's what these longitude and latitude are bunched up for. Here's the median age of houses. It looks pretty good, although this lump at 50 probably means that there's just a maximum age, and everything over 50 is just treated as 50. So that might be a defect in the data that might hurt us. And there's other things here, other populations. Some of these look like relatively not normal, but say Gauss. There's these curves that do this, the Cauchy curves, I think. Anyway, the fairly common distributions. All right. So that gives you can look at what kind of data there is there. So now you break it up into training and test sets again. So 20% of it is reserved for testing the model later, and 80% is used for training. And you've got the start of the test set. All right, showing, and it shows all the columns here, the first 5 records with all 10 columns. All right. And if you run it again, you'll get different rows selected each time. It's making a random sorting in a training and test set. All right, now there's a problem with bias sampling. This is also what happens with polls. If you just make so consider this simpler problem. We're going to do something like a survey of people, and women and men are different. So let's assume 51% of the population is female and the rest are male. So if this is true, then if you make 100 random samples of 1,000 people, how many females do you get in each sample? And you can make a chart, and you'll see the most likely thing is you get the right number, 511, but you have a chance of getting as many as 540 or as few as 475 females. And if you randomly get a sample like that, that sample is not really representative of the whole. This is a problem in all sampling, and the same thing is true of political surveys, polls they do to like predict the president. It's just a random sampling is not really the best way to represent the population. If you have a parameter that you feel like is important for the result. So you want to do what's called stratified sampling. So we feel like, for example, median income probably affects housing price. If there's an area where people have a higher income, they probably buy more expensive houses. That seems reasonable, so you probably don't want to let median income be randomly sampled. So what you're going to do is break it into 5 categories. 0 to 1.5, 1.5 to 3, and I forget what units this is in, but anyway, 4, 5, 6, and greater than 6. So we break it into 5 categories, and then we can make a histogram. So here's how many districts there are in those 5 categories. So here's 5 categories of income with a reasonable number of districts in each one. And now we can see the first 5 rows of the data set. And as you can see, we've now added a column called income category here, 5, 5, 4, 3, to the data set with the previous calculation. So now there's 11 columns. And now we can split the data. We're going to do the splitting into training and testing set again, but this time we're going to do stratified splitting, which will take each of those 5 categories and take 20% of it and then add it together. So this will make the stratified test set. And you can compare the two here. So the training set, if you count how many of the different categories there are, they're like this. And the test set is down here. Now this is the, so the training set is 35% category 3, and the test set is 35%. It's 3.9% of category 1. This is 3.9%. You can see this stratified sampling makes sure that the test set has exactly the right amount of each of these 5 categories to a very close match. If you want to compare a random set, you can do the same calculation there, and you can see how wrong it might be. For example, it's supposed to be 0.115, but I really only have 0.110 of those. And this one's supposed to be 316, but I really have 326. This one's supposed to be 351, but I really have 347. So that's why random sampling is not the best way to go. The stratified sampling is a better representation of the real data. All right. So now we can remove that column. Now that we've used it, we have the training and testing set. And then you can visualize the data. You can plot it by latitude and longitude. So if you do, you get a map of California with a blue dot for every zone. The problem is when the blue dots overlap, it's hard to tell how many blue dots there really are there. So it would be good to add transparency to it with alpha. You set alpha equal to 0.2, and now the dots are transparent, so you can see where the dots are sparse and where they're dense, they pile up, which is, of course, near San Francisco, near Los Angeles, and somewhere in the Central Valley where you have a lot of houses. And you can include population and price with color bars and such. You can make a nice colorful chart here where the price is indicated by the color, and you have population is the size of the dot, and now you have a nice chart of California showing all these things. So these are just tricks to manipulate data to understand it. You can do correlations between the data to find out which ones are more important. Here's the correlation of the output we're trying to predict, which is the median housing cost, from the others. So of course we're trying to predict median house, so that's 100% correlated with median house. That's something to itself. A correlation coefficient of 1 means that if you increase that parameter, it increases the housing price. And so you see median income has a really strong correlation, 68%. As you would think, when the income is higher, the housing price is higher. Total number of rooms has some correlation, and so does median age. Then you get down to the small change. None of these parameters really matter much at all. And then latitude has a negative correlation, which I think is just declaring latitude and longitude. That's east-west, showing that I think the areas on the coast are probably more expensive than the areas inland, is all you're seeing there. So that's the number here. Now you can make scatter plots to see that. And so here on the diagonals, you get histograms of each of these. So here's the median house value. And here you get house value as a function of median income. And you can see a few things to see here. As the income goes up, the housing price goes up, which is what you'd expect. Here's the other parameters that showed some correlation, but not much real pattern here. The top row is all that's worth looking at here, because we're just trying to predict the house value. And so now you can blow up this one in more detail, which is the one of interest, how income affects housing price. And here you can see important things. Not only is there the general trend that this goes up with that, but you can see errors in the data. There's apparently a maximum house value and a ram up of data here, which is probably not really accurate. There are these weird horizontal lines which indicate peculiarities in the training set that probably really don't reflect the real world. And I don't know what this is. It could be errors in the test. It could be like there could be one housing development that sells a whole bunch of houses all at the same price, regardless of your income or something. But these are the kind of quirks which probably don't really represent the real trend. And you probably don't want to include them in the model. So you might remove these. So this is when I used to do science, people argued about this. You would do measurements, and there were some people that did this. They would remove the outliers before fitting curves. But that's what's happening here. That's what they do in machine learning. So you can also you can create new columns. For example, rooms per house. You can take rooms divided by number of households, and you can have bedrooms per house, and you can have people per house to create new columns, and combining columns might have something more important. And in fact, that's what happens. You will see, I got to have a little more explanation, but you'll see here is that rooms per house is 14% correlated, but rooms is only 13, and number of households is only 0.07. So this is often the case. If you use intelligence, you can make a combined field that is a better predictor than either field would be alone. So this is the kind of thing where it really becomes this is where you start messing with the data and changing the parameters, and that's where you have to feed in actual evidence and information about how it works. So the model is not 100% learning, you're feeding in some knowledge. So this is where it gets pretty touchy. But anyway, there's attribute combinations, and there's more. But anyway, that's some of the things you do to massage data. Another thing that's not in here yet, but will matter, is you normalize data. So that it always goes from 0 to 1, which greatly improves the accuracy of a lot of these learning algorithms. Anyway, that's the kind of detail you get from the second book. And I've got one more of these to talk about.